Welcome back to our series on statistical mechanics. In the previous episode, we were discussing canonical ensemble and its various case studies. We discussed about its partition function and we took 2 or 3 examples which deals with the canonical ensemble situations. There we had discussed about both the classical and the quantum mechanical cases for in order to explain the partition function and its relevance in the context of canonical ensembles. Today in this episode, we will be discussing about the grand canonical ensemble. If we remember, in the beginning of this series on statistical mechanics, we had one of the episode specifically on different kinds of ensembles and its characteristics. There we had told that there are 3 kinds of ensembles, microcanonical, canonical and grand canonical ensembles. If you remember, again the grand canonical ensemble means that you are allowing a situation where you are where you are allowed to change both the number of particles and the energy. So, if you contrast with the case which we discussed in the previous episodes, which is about the canonical ensemble, there it was only energy being allowed to vary, whereas here in the grand canonical ensemble, you are allowing both the number of particles and the energy to vary. Before watching this episode, it would be useful for the students to have a relook through the canonical ensemble and its initial episode, because the derivations or the discussions about the grand canonical ensembles are very much similar to the canonical ensemble situation. But here the partition functions are different. Here we are introducing a new thing, a new parameter called the Q potential. All those things will come around, but basically the approach towards both the kinds of ensembles are pretty similar for the convenience of the learners. Now, having said that, similar to the case of canonical ensemble, let us assume that we have a box full of different microstates, right. So, there are omega number of microstates, and if you let us put the entire system, designate the entire system by A0, and the total number of particles are N0 and the total energy is E0. So, this is the total characteristics of this box, and within this box let us imagine an area A, right. Let us imagine a small area A, and A is having nr number of particles, and Er is the energy of the microstates in that area, sorry, the Es, nr and Es. Es is the energy of the particles in that the small area A, and the rest of the area I will designate it by A dash, which is having nr dash number of particles and Es dash energy. So, this is the situation which we are dealing with, and you know that similar to the canonical ensemble, this is a case of heat reservoir, right. Heat reservoir means the system, the box is having immense capacity to compensate for the any kind of temperature changes in the system, which means what? which means that at thermal equilibrium both A and A dash are in a common temperature T. Okay. So, both A and A dash are in the same temperature. This is a general characteristic of the ensemble, to remind you, because we always tell it in terms of NVT, right. We are whenever we define a macro state, we define it in terms of NVT. But here in this case we are allowing N to vary inside the box of microstates, but outside the box these parameters are same, right. So, that is one thing which you have to remember. Okay. So, so that is the case in which we will be dealing, and now similar to the earlier discussions on the canonical ensemble, here also we can assume that the minimum and the maximum values of the energy. What is that minimum and maximum values of the energy? We can write that 0 less than or equal to Es less than or equal to E0, right. This is the minimum and maximum energy, and and corresponding number of particles I can write 0 some more less than or equal to Nr less than or equal to is N0. So, these are the conditions in which the system A will work, right. And similarly, for the A dash also you can similarly write this as equal to 0 less than or equal to Es dash less than or equal to E0, and what for the number of particles it varies between 0 to 0 to N0. So, this is a situation for A dash. Now, what else we need to tell? Now, we need to introduce a probability, right. What is that probability we designate? We designate it by PRS. Earlier in the canonical ensemble we were denoting by PR, here we have PRS. So, what is PRS? PRS is the probability for the system A to be any one of the states characterized by the energy value Es and the number of particles Nr, right. So, PRS is actually connected to the small area which we took, which is corresponding to A, and PRS represents the probability that this A is having an energy Es and number of particles Nr. Okay. Now, how do we further our knowledge on the PRS? I can write always PRS is directly proportional to omega Nr Es, right. That is very simple claim to write. We have done a similar argument in the case of canonical ensembles also, where omega represents the number of microstates. Okay. And there in the case of canonical ensemble, similar to those situations, we have to invoke some kind of a argument. There in that episode I have detailed on that is what I remember. Basically, since this is a very small number, right, because in the bigger volume I am taking only a small volume which is A within the box A0, but this this calculation of the probability will be more accurate instead of the omega NRES if I take the probability of the number of particles and the energy ES dash in the area outside the small area A, right, because this area is very much small or even negligibly small compared to A dash. Since this is a very small area, the chance of getting error in the PRS will be more, and therefore, it would be safe more for me to take instead of PRS, I would take instead of say P dash RS, right, which is corresponding to the volume A dash. Now, therefore what? Therefore, I can write this proportionality is actually proportional to omega dash NR dash S dash, right. I think it would be better for me to keep the same kind of designation NR ES NR dash S dash, right, which is actually what I can always write it in terms of the identity which we had written over here, which is what that I didn't wrote here, which is NR. Here I should write about this system as NR plus NR dash is equal to N0. ES plus ES dash is equal to E0. So, I can always represent this NR dash in terms of N0 and NR, because it is again a subtraction. NR dash is equal to N0 minus NR, and E0 and ES dash is equal to E0 minus ES. I am very safe to make such kind of adjustments in this equation. All those things are equivalent. Now what? Now for PRS we are going to take up this expression. Now the next thing to assume is that this omega dash NR dash ES dash will be a fastly varying function, right, or a rapidly varying function. Again, when we are dealing with a rapidly varying function, for a mathematical approximation, or if you go back to your 12th class, if you take the 12th standard textbook, if you want to assume to a polynomial approximation, it would be always safer for us to take a slowly varying function, right, because not connected to statistical mechanics per se. If you want to approximate to this kind of a function, for me mathematically it would be it would be better if I say I project it slowly so that this function can be repeated in the correct manner. If the more faster varying function I use, the more error will be getting into this expression. So, this kind of an assumption is to be utilized here. So, how do we make this function a slowly varying function? What I will do is that I will make this function a logarithmic function, right. So, instead of omega dash, I will be using logarithm ln of omega dash NR dash ES dash. So, for the rest of the mathematical operation I will be using the logarithmic function, but you have to remember yourself that you have put an additional logarithm over here, which means that in the final expression I have to take out that logarithm, which means that I have to convert it to an exponential function, right. So, that we have to be careful about. So, what is the function which we will use so that we can approximate this situation? Similar to the case of canonical ensemble, we will use the Taylor series. Right? What is Taylor series? Taylor series, if you remember, we have a function fx is equal to f of a plus x minus a into f dash a by 1 factorial, right, plus x minus a the whole squared f double dash a by 2 factorial, and so on and so forth. It goes like that, right. So, this is the very famous Taylor series. So, we will use this Taylor series to make this approximation. So, while using this Taylor series, I have to be I have to tell you what is the value, what is the x which represents, what is the a value which represents. Here in the case of here we have two parameters, unlike the case of canonical ensemble, here we have two parameters, one is the energy and another is the number of particles, and therefore, I can write x is equal to what Es dash, and x is equal to Es dash, and a is equal to what, my E0, right. X is equal to Es dash and a is equal to E0 when we are dealing with the energy part, and if when we are dealing with the number of particles, x is equal to x is equal to nr dash and a is equal to n0, right. So, these are the two ways in which we have to carry out this Taylor series expansion. So, what all we have done? We have made the function varying slowly with the logarithm, and then we are using this Taylor series to make this operation on this logarithmic function. So, when we are doing this operation, I can write this as equal to ln of omega dash Es dash nr dash is equal to what? Ln of ln of omega dash E0 N0 plus I have the differential functions. So, here I have to carry out the differentiation in terms of two parameters, one is the number of particles and another is the energy. So, when I carry out the differentiation, I have to write dou ln of omega by dou n and then we can write it in terms of the nr and n0, which I have as I denoted in the previous slide, right. Here we have the nr dash and n0. So, therefore, we have to put that over there plus dou ln omega by dou E dash Es dash minus E0 plus etc. So, here we are taking only the single differentiation, and therefore, we can continue with that. But as the bigger parameters get smaller, we can always we can always delete or neglect those functions and limit ourselves to these three terms. And if you analyze this one, this first term over here is a constant, right? Because why? Because as I told in the beginning, the box in which we are doing this analysis, there is no, we are not allowing any number or any particle to enter or leave the system. Energy needs to be constant there, right, when we are looking from outside. So, therefore, this value will be a constant. And what is this value? Nr dash minus N0 means my minus Nr, right. So, I can write this as equal to dou of ln omega by dou n dash minus Nr, and this will be minus Es, right. And if you remember our discussions on the initial episodes of this series, we have defined 2-3 functions, right. So, dou ln omega by dou E dash, dou E is actually beta, which we have, that is a part of the definition of the function of beta, and dou ln omega by n dash is defined as Z, or 1 by the, or mu by kt, right. So, mu by kt is we can always write it in terms of that function, and therefore, I can write this as equal to a constant, right, constant plus mu by kt plus beta is again 1 by kt, that should be minus 1 by kt, right, minus in terms of the energy, therefore, minus 1 by kt yes, right. Sorry, there was plus mu by kt nr minus 1 by kt Es. So, this I can, this if I remember, this is the expansion for my ln of omega dash, right, which means that I need to cancel out that logarithm which I applied, which means that I need to take the exponential of that one. So, therefore, I will rewrite that expression as PRS is now proportional to exponential, so that I cancel this logarithm which I introduced, exponential minus alpha nr. What was the alpha? Alpha is equal to minus mu by kt, which we have discussed in the one of the initial episodes. So, alpha is equal to minus mu by kt, and mu is what? Mu is the chemical potential of the system. There I have explained what does the chemical potential means by. So, alpha is equal to minus mu by kt. Therefore, here in this here I can write exponential minus alpha nr, 1 by kt is what? Beta. Therefore, this is minus beta yes. So, PRS is directly proportional to exponential minus alpha nr minus beta es, right. Now, we have this equation, but this is having a constant of this is having a proportionality, and therefore, we need to we need to normalize on this equation, and therefore, I can write PRS is equal to, as a normalization function, what I will do is that I will I will make a summation on this one, right. Therefore, exponential minus alpha nr minus beta Es divided by sum over exponential minus alpha nr minus beta Es. Now, if I make the summation over PRS, what is the summation over PRS means by? Summation over PRS means I am summing all the probabilities, summing out the probability of the whole situation of all the boxes together, of all the energy levels and the all the micro states together. Therefore, sum over PRS is equal to 1. So, therefore, if I take the summation over here, right, this will be 1. That means, now I have a constant which is equal to sum over exponential minus alpha nr minus beta Es, which means that this constant, now I can take this as equal to C. C is equal to 1 by sum over exponential minus alpha nr minus beta Es. Okay. So, that is the discussion on that is the introductory discussions on the grand canonical ensemble. So, we have defined what does a grand canonical ensemble means by, what is the value of the probability or how can we evaluate the probability that a particular volume is having an energy level Er and Ns, and that is given by this expression. And so, with this knowledge we will be able to discuss more into the grand canonical ensembles, especially we need to find out its partition function, which we will be doing in the next episode. Thank you.